students, in physics, in the section waves and oscillation, now let's see another experiment. Yeah. What is this experiment? Determination of the velocity of sound in air using a closed resonance tube and a set of tuning forks, and also determination of the end correction of the tube. Right. Previous experiment we saw using only one tuning fork how to find the velocity. Here we have a set of tuning forks. So what we are going to do here, it's very simple. Like we did in the previous experiment, we will make the arrangement for a resonance tube with variable length, right? This is water, and then you take each tuning fork, vibrate it and keep it here, and start from the smallest air column and increase it slowly. When you get the first resonance, that means when you get the increased sound from the tube, that means resonance happens. When first instance, when you are increasing the height from 0 and first time when you hear the resonance, right, what you see there is the fundamental note like this, right. So now we can say this L is going to be lambda by 4. So lambda is 4L. V equals F lambda, F is known, F into 4L. We have a set of tuning forks, which means we have different frequencies. So we can go for a graphical method. How? L equals V by 4 into 1 over F. Y equals mx. Right? Change the frequency and get different L values, and you can find the velocity using the gradient. Okay. But then there is this concept of end correction. What is end correction? See, this side is anyway closed because you have water there, but on the other side, since it is open, the antinode, here you get a node, you call this a node, and the antinode may not be exactly at the brim of the tube, right. It might be sometimes outside the tube as well, because the molecules there, air molecules there, are free to mobilize, free to move. So what happens sometimes, right, we may have it like this. So if you look at it closely, the tube is there only up to here. So the L is only this much, but your lambda by 4 goes passing that, which we call the end correction E. Now the lambda is going to be, or lambda by 4 is going to be not L, it's going to be L plus E. It's going to be L plus E. Understand? So if I rewrite this formula, instead of L, if I write L plus E, right, we can write here V equals F 4L plus E. From this you will get L equals, this will come down here, V by 4F, V by 4 into 1 over F, let's say, into 1 over F. This E will go to the other side as minus C. Y equals mx minus C. So with a minus intercept, you get a graph. With a minus negative intercept, you get a graph. Intercept will give you the end correction. End correction may not be there sometimes. Sometimes it will be there. So we don't know. We will take it as E and see how much end correction we get. From the gradient, we can find velocity. This is what the simple experiment is. All other procedures, everything is same as earlier. Just one more thing you have to understand. Here we say, where L and 1 over F are proportionate, right? If I ignore E, then we have this. That means when F reduces, L increases, correct? Inverse proportion. So when we do this experiment, to find this length, first we will take the highest frequency. right, highest frequency. Let's say we have 512 hertz, 480 hertz, 420 hertz. Likewise, if we have the frequencies, first we will do the experiment for this one. When we do for this one, we will keep the air column as low as possible, maybe at 0 level itself. That means the water level must be at the top of the tube has to be submerged in the water, almost at the same level of water, the tube will be there. Then slowly you increase, find the resonance length. Then, suppose let's say this is the length you have got. When you do it for 480 hertz, you don't have to restart. You can continue from this point onwards, because for 480 hertz, resonance length has to be more than the resonance length for 512 hertz. Because when frequency reduces, resonance length increases. Do you understand? Therefore, when we do this experiment, we will arrange the tuning forks in the descending order of frequency. And in that order only we will be doing the experiment, so that we can get the fundamental note for all of them comfortably, very easily we can get. Otherwise, what if you mix up the frequencies, for each and every tuning fork, you have to start from 0 height of the air column and increase it. So, it can take a lot of time for you to do the experiment, right. That is why we start with the highest frequency, find the length of resonance. From that point onwards, you can move to the next frequency, because that is a lower frequency. Get it? Look at the materials and apparatus required for this experiment. A tube of diameter about 2.5 centimeter and length about 50 centimeter. A set of tuning forks of known frequencies. We should know the frequencies, because when you draw the graph, 1 over f is going to be the x-axis. A half meter ruler to measure the length of resonance. A tall jar and a stand. A tall jar is for this. This is the jar, you know that. That is also another PVC pipe, but we call it a jar with water. And a stand to fix these. Look at this same arrangement we have again, right. I already explained what we are going to do here. When a closed tube is resonating at the fundamental note, let lambda be the wavelength of the wave, L the length of the resonating air column, and E the end correction of the tube. L plus E equals lambda by 4. I explained it. If V is the velocity of sound in air, F the frequency of the fundamental note, then lambda equals V by F, right. For lambda, you can put 4L plus E, rearrange it. This is what we have. So, this is what I am going to write in the y-axis, x-axis, M and C. Gradient of the graph of L against 1 over F is going to be V by 4. L against 1 by F is going to be V by 4. V is gradient into 4 and E is the intercept. Careful, it will be a minus intercept. So, we have to take value of E, value of E, or value of intercept. Intercept is going to be a minus intercept. Take the value of it, that will give you E. As shown in figure, immerse the tube vertically in the water contained in the jar, leaving a small length of air column, and fix the tube onto the stand. Select the tuning fork of highest frequency from the set, vibrate it and hold it just above the open end of the tube. Then raise the tube and the tuning fork together until a louder sound is heard for the first time, indicating fundamental resonance. Same thing we did for the previous experiment as well. There we did with one tube or one tuning fork. Here we have multiple tuning forks. Measure the length L of the air column above the level of water in the tube and note it along with the frequency F of the tuning fork. Selecting the other tuning forks in the descending order of frequencies, obtain fundamental resonance length L relevant to the frequency F of the tuning fork used as done above, and after obtaining about 5 sets of readings, record the values. Right. So, it is quite simple, no complication. Let us see how we can do this experiment now. The apparatus required for this experiment include one jar of water, one jar with water. So, even though we call it a jar, it is actually a pipe, a plastic pipe which has been closed in one end, and we have filled it with water. Up to here we have filled it with water, right. It is a jar with water is what we say, or you can even say a pipe with one end closed, or a tube with one end closed. Then this is the resonance tube.
right? 50 centimeter length approximately. That's the resonance tube. You know how we are going to close one end of it. You immerse this into this jar of water, then one end will be closed, other end will be open. By adjusting the height of this resonance tube, you can change the length of air column that is going to resonate with the tuning forks. This is the set of tuning forks, right? This is the set of tuning forks we are going to use. We are using 5 different tuning forks. We know the frequency of each of them, right? Tuning forks with known frequency. And this is the hammer with rubber head. You know, we have to use a soft surface to vibrate these tuning forks. If you use hard surfaces, it might damage the properties of the tuning fork. So that's why we use this hammer with rubber head. And we use a meter ruler to measure the length of resonance tube. When the resonance takes place for each frequency, we need to measure the length of air column actually. Length of air column that resonates means above the water level, how much of length is there for the resonance tube. That's what we call the air column that resonates. To fix the meter ruler, we are using a stand. Right, this is the stand we are using to fix the meter ruler. This is all the apparatus we are going to use in this experiment. Let's see how we are going to fix it. First, let me take the meter ruler, and fix it inside. So, I am keeping it inside the water jar. Make sure it's vertical. Then let me keep the resonance tube inside the water jar. You know the experiment steps because we have done the similar steps in the previous experiment also. What are we going to do? We will take each of these tuning forks, right? We will vibrate it. We will keep it close to the end, open end of this resonant tube. Increase the length of it, increase the height of it, or basically raise it, and find the point where you hear highly intense sound. The level of intensity of sound will be very high at one particular point only. That reflects the resonance happening at that point. Then you can measure or you can read the reading of this point, and then you can check at what level water is there. The difference between the two readings is going to be the resonance, or the length of air column that is resonating. And when we are doing it, usually, see what we are going to do here is to find the fundamental overnote, right? Fundamental overtone, right? Fundamental note or fundamental overtone. So what we do, we usually start with the highest frequency. You start with the highest frequency and keep this length as short as possible and slowly increase it. First time you hear the high intensity level of sound, that reflects the fundamental note. You can measure the length of air column that resonates. Why did I take the highest frequency? Because then the next frequency is going to be lower than the first frequency. When the frequency reduces, lambda will increase. Lambda increases means I can expect the next frequency's resonance to happen at a higher length than the previous air column's length, right? So we can start with the highest frequency and little by little we can reduce the frequency, little by little we can reduce the frequency so that lambda increases, so that L also increases here, right? That's how we do the experiment. What will happen if you randomly take the frequencies and if you find where the resonance happens, you can't ensure the resonance you identify, the point where you think the resonance happens is the fundamental note. Sometimes it can be the first overtone as well. So to ensure it's the fundamental note, you have to start with the highest frequency, not only highest frequency, keep it closer, the length of air column, keep it as short as possible, then slowly increase it, find the first point. After that, reduce the frequency, that means take a different tuning fork with lower frequency, and from the first frequencies, previous frequencies resonant point, slowly increase the height. This is how we are going to do it. And as I always say, when we do these experiments, we have to keep the ear closer to the resonance tube. the end of resonance tube and we have to observe that sound, because even though we say high intensity level of sound, compared to the environmental noise, sometimes you may not be able to observe it, you may not be able to listen. Therefore, ensure you are in a quiet environment, there is no other noise to disturb, otherwise you will not find the exact point where the resonance happens. But in this experiment here, when I am doing it, I am not going to keep my ear here and do it. I am going to fix a microphone. I will fix a microphone to this top open end of the tube. I am going to fix a microphone so that you can hear the resonance sound very clearly through the microphone. Otherwise, we have to keep the ear like this and slowly we have to increase height to find where the resonance happens. That's how we usually do in the lab. But here, I am going to use a microphone to give you the experience of doing the experiment, to give you the experience of listening to that resonance sound, right? So, let us fix the microphone now. Now, you can see I have fixed the microphone here, you can see that. I have fixed the microphone here, so you can hear the sound clearly. You can hear the sound clearly, this is the microphone for you, yes, right. So, I have taken the highest frequency now, this is 512 hertz, this is 512 hertz, right. I do not have to keep it too close to the water level because we know it is around 10 centimeter or beyond that only we are going to get it. So, approximately it is going to be above 10 centimeter we know, that is why I am starting somewhere at this point. You can hear somewhere there I heard the high intensity level of sound. That is the point I am hearing it. Once more, shall we check it again? You can see this is the point where we hear the highest sound. That means at this point, get the reading here, the open end of the resonance tube, this is at 56.5 centimeter, 56.5 centimeter, right? And the water level is at 42 centimeters. 56.5, 42, the difference is 14.5 centimeters. So, when I use 512 hertz, the resonance happens at 14.5 centimeter length of air column, right, that is for 512 hertz. I will show it once again to you, you can observe it very clearly, look at this. Can you see? Below the point, it is low. When you go up also, it reduces. This is the point where it is maximum. This is at 56.5 centimeters. So, 56.5 minus 42, 14.5 centimeters we get. Let us write down all these readings because we are going to go for a graphical method. Let us write down all the readings one by one. First one, 512 hertz, 14.5 centimeters. 512 hertz, 14.5 centimeter. Next one, as I mentioned earlier, we started with the highest frequency. From that, we are going to go in the decreasing order, right? Descending order of frequency. The next one is at 480 hertz, 480 hertz. Now, see, we have got the resonance for the first one at 56.5. So, surely when I use a lower frequency, the length has to be higher. So, I can start from 56.5 when I do it for the second frequency. Yes? Can you see? See, that is the point where we get the maximum. Once again, $57.5. When it is at 57.5, you hear the maximum sound. How do you ensure that is the point where it is maximum? If you go passing that point, the sound reduces. Before the point also, sound reduces. At 57.5 is where we got the maximum sound. 57.5, the water level still at 42, right? 42, 57.5 means 15.5 centimeters. Let us write down that as well. The frequency I use this time, 480 hertz, 15.5 centimeters. 480 hertz, 15.5 centimeter is the length of air column that resonates. The next one has to be a lower frequency than 480. What I have is 426.6 hertz, 426.6. I can start from where the previous resonance happened. It was at 57.5, isn't it? Yes. So, from there, approximately from 57, I am starting. Can you see? This is where the maximum sound you can hear. Once again, close to 60. Not exactly 60, but then we don't have any measures before 59.5. Look at this again. Close to 60. It's almost 60. 60. When it is 60, check the water level, because water level can change when you raise this tube up. The water level can go down because the displaced water is going to be less. Yes, as expected, it has come to 41.5 centimeters now. 41.5, this is 60, that means 18.5 centimeters difference. 41.5 is the water level, that means closed end of this resonance tube is at 41.5, open end is at 60, 18.5 centimeters is the length of air column that resonates. This is for the frequency 426.6 hertz. 426.6 hertz. 18.5 centimeter is the length we have got. Next one. We have 384 hertz. We have 384 hertz. So, this was at 60. I can actually start from 60 itself. Can you hear at some point its maximum once again? This is the point where it is maximum. The reading is at 62 centimeters. 62 centimeters. 62. Check the water level. Water level is at 41.5. 62, 41.5 means the difference is 20.5. 20.5. 20.5, that is for what frequency? That is for 384 hertz. 384 hertz. 384 hertz. We got 20.5 centimeter. We got 4 readings. Better if we have 5 readings for a straight line graph. Next one we have 341 hertz. 341 hertz. So, this was at 62. So, let me start from 62 itself. Let me start from 62 itself. Can you see? Again, can you hear that again? That's the point where it is maximum. That's at 64 centimeters. That comes at 64.5 centimeters. 64.5 centimeters. Make sure when you are getting the readings, your eye level and the reading level must be at the same level, right? You should not be observing it from a lower point or higher point, then the readings will be different. So, it is at 64.5, at the same level I am reading it 64.5, and the water level is at 41.5. 41.5, right. So, we got 64.5, 41.5 means 23 centimeters we are getting, 23 centimeters we are getting. That is for 341.3 hertz, 341.3 hertz, 23 centimeters we get. Now, we have got 5 frequencies and the length of air column for which the first or for which the fundamental note is observed. First time we are listening to the resonance beams, we are able to observe the resonance beams. That's a fundamental note. Fundamental note L we have observed, we have calculated that can include the end correction as well, right. So, let us bring these 5 values, let us do the calculations, let us draw the graph. Without correction, it has to be y equals mx, but with correction, it can be y equals mx plus c as well. From the gradient, we can find the velocity of sound. From the intercept, we can find the end correction. Now, let us draw the graph and see what values we are getting for V and E as well.
You all can see that I have recorded the readings that we have got. These are the frequencies that we used, and the fundamental resonance length we have got this. Frequencies I have found the inverted values 1 over f also I have calculated and I have included here. Now, we need to draw the graph. You remember the equation again? What? L equals V by 4 1 over f minus E, y m x c, correct? Let us draw the graph and see. Right, this is where we have 1 over f, which is in hertz minus 1, no, into 10 to the power minus 3 hertz minus 1. And the L is in centimeters. Right, before you draw any graph, make sure you mark the axis, yeah. 0, 0. The x-axis we need up to 2.93, 2.93, 2.93, 1, 2, 3, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 25 is what we have. Then what we will do, we will take 1.5 by 1.5, 3, 0.6, 0.9, 1.2, 1.5, 1.8, 2.1, 2.4, 2.73. The y-axis we need up to 23 centimeters. 23 is in all whole numbers, so we have 0.5s also, right? 1 by 1 we can't take it, we will take 2 by 2, 4, 8, 12, 16, 20, 24. First point is 14.5, 1.95, 1.95, 1.95, 1.8, 1.95 is this line, 14.5, 12, 14, 14.5. 14 is here, 14.5, 14.5, yes, 2.08, 15.5, 2.08, so almost here, 15.5, right, 15.5. 18.5, 2.34, 2.34, 18.5, 2.1, 2.25, 2.34, 2.25, yes, 2.34. That's at 18.5. 18.5, 16, 18.5, 2.34. That's how that value will be. Next, 2.6, 20.5, 2.6, 2.4, 2.55, 2.6, 20.5, 20.5, 2.6, 2.4, 2.55. Check this, 2.34, is that right? 2.34, 2.1, the 18.5, the 2.34. Seems we made a mistake. 2.1, 2.34 is here. 16, 18.5, like that. Next one is 2.6, 20.5, is it? 2.6, 20.5, 2.4, 2.55, 2.6, 20.5. Yes, if you have a graph sheet, you can mark these better, but these values anyway. 2.93, 23, 2.93, 2.7, 2.85, 2.93, 23, 22, 23. Right, that's how we are getting the values. Let's draw the graph and see what happens. Yeah, right. Now, to find the intercept, we need 2 points. Maybe this point seems to be good here. Can you see it goes through the intersection? That's going to be 2.1 and 16. And we need another point. We can take this point. This is good. 0.45 and 2. 0.45 and 2. So let's take the gradient. We'll mark the intercept also. Intercept is almost minus 2, isn't it? Minus 2. Minus 2. You know, E is the value of intercept. Let me put a mod sign to say it's the value of intercept, not the minus sign. So it's 2 centimeter we have got. And then the gradient, which is V by 4, 16 minus 2, that's in centimeters. Convert that to meter, over 2.1 minus 0.45 into 10 to the power minus 3. Don't forget that. So that you get, this is 14 minus 3 minus 2, 110 will go up, 140 divided by, this is going to be 1.65. So V will be equal to, multiply that by 4 also, 560 divided by 1.65. Let's divide and see. 560. Let me put 2 more zeros. Oh wait, we can divide that by 5 maybe. 112, 33. So it's at 11200 divided by 33. 4 is not enough, 3, 99, 13, 130, 4 still not enough, 3, 99, 31, 310 will give you around 7, 8, 9, 339. Yeah, so approximately you get 339 ms minus 2. Which is very close to the theoretical value. We say it's around 340. It's very close to the theoretical value. 339 meter per second. Meter per second, not second squared. It's velocity or speed, meter per second. Understood? Right. So that's a very simple experiment. I have shown you the steps clearly. Please go through the experimental procedures couple of times for you to remember, understand and remember, not just memorize what you memorize from a book. Understand and remember what we are doing. Then whatever the different questions you get in the exam should be simple to answer. Clear? Now what we will do, we will take the past paper questions on this experiment and see how we can answer that. Let's see some past paper questions from this experiment. First one I have taken from 2011. When a tuning fork is at resonance with a tube with one end closed, what is the type of the wave being produced in the tube? Longitudinal or transverse, traveling or standing? So you know the air molecules or the particles, they vibrate in a longitudinal wave, and what we get is a standing wave as well, right? Longitudinal and standing wave. Next, you are provided with a set of tuning forks of frequencies 288 Hz, 320 Hz, 362, 480, suitable glass tube, a glass jar and other necessary items to determine the speed of sound in air using graphical method. What is the purpose of immersing the tube in water? To close one end and get adjustable length of air column, right? To obtain a one end closed tube with adjustable length, Inside the tube shown in the diagram, draw the wave pattern of the mode of vibration that you would set up for taking data. Clearly indicate the end correction in the diagram. That's how it's going to be. So whatever the length outside is E. Let's mark like this. This is E. That's E. Right? This length. Which tuning fork would you select first to take data? Give the reasons for your selection. You all know that L is proportionate to 1 over F. So what we do, we usually take the highest frequency first. That will have the shortest length of resonance. Then when you take the following frequency, the next higher frequency, the length has to be a little more than that. When you take the next frequency a bit lower than that, let's say you are starting with 512 Hertz, you got L1. Now if you take 480 Hertz, the length has to be greater than length 1. So the advantage is, you start from 0 length, for the highest frequency you find the resonance, and when you do it for the second frequency, you don't again have to start from 0 length. You can start from where you stopped for the previous one, because we know for sure second length has to be bigger than the first length because the frequency is less. So that's why they are asking which one will you take first, give reasons for your selection. So what are the frequencies given to us? You have highest is 480 Hertz. 480 Hertz. We can say this will have shortest resonance length. Resonance length. When forks are taken in descending order of frequency. Descending order of frequency. The lengths will be in ascending order. Understand? For this purpose only We take the highest frequency first. Next, calculate the minimum length of the glass tube required to take data using the given set of tuning forks. Take the value of V in air as 345.6. So, look at this, V is F lambda 4L. Why? Lambda by 4 is going to be L, ignoring E. Then L will be V by 4F. So, if you want to get the highest length, take the lowest frequency. V is 345.6. For what's the lowest frequency they have given? 288 Hertz. 288. 71, 8, 32, 25, 6.4. Then again we can cut by 4, 2, 1.6. Now 216 divided by 71, you have 3, 0.30. 0.30 meter. That is 30 centimeter. So, if you can have 30 centimeter long tube, then for all these frequencies you can get sufficient, you will have sufficient length to get the resonance. Why? I have taken the lowest frequency. Why? L is proportionate to 1 over F. So, when F is low, L is going to be high. So, if the lowest frequency has sufficient length, definitely other frequencies also will have sufficient length. Right. Obtain the necessary equation in terms of F and the resonance length L to determine V and E by plotting a graph. Right. Now, we can say V equals F lambda. V equals F into 4 L plus E it is going to be. Why? Lambda by 4 is going to be L plus E. L plus E. So, from this you get V equal 4F, V over 4F equals L plus E. L equals V by 4 into 1 over F minus E. Y M X C. If you are asked to use another tuning fork in addition to the tuning forks given in B above to do experiment, which one out of the given set below would you select, considering the requirement to have a uniform distribution of points on the plot? Now, see, what are the ones we have already? Which ones do we have already? 320, 288, 320, 362, 480. We have 288, 320, 362 and 480. So, what we are going to have in the x-axis is 1 over f. So, good if we can have the 1 over f values almost in equal interval rather than they are concentrated towards one side. Equal interval or approximately equal interval will be good. From here to here you have 0.4. Then from here to here you have 0.3. From here to here you have 0.7. So, good if we can have something in between these two, because 0.4, 0.3 in that range, right. Then this must be 2.5. This is 2.5, yeah. So, if you look at the difference here, look at this. If I take these two, then 2.8 to 2.5 you will have 0.3 difference, 2.5 to 2.1 you will have 0.4 difference. So, which is the similar differences we had earlier, 0.3, 0.4 differences you will have the points. But if you take the other one, so if you take these two, then the difference is going to be 0.5 here and then 0.2 here. So, that is not evenly divided, isn't it? 0.5, 0.2 compared to that 0.4, 0.3 is better, which means 406.4 Hertz would be ideal. Which one would you select? 406.4 Hertz. And they have clearly mentioned to have a uniform distribution. They have mentioned that. Next. Draw a rough sketch of the graph that you would expect in this experiment in the following figure. Label the axis. The dependent variable should be on the vertical axis. Dependent variable is L. This is 1 over F. The graph we get must be like this, because it has a negative intercept, in the room temperature was uniformly increasing during the period of data taking the curve that you would expect theoretically on the same figure above. If the room temperature was uniformly increasing during the period of data taking, draw the curve that you would expect theoretically on the same figure above. So, what will happen when the temperature increases? When temperature increases, velocity will increase. Right? When velocity increases, the L values also will increase. Why? V equals F lambda. Lambda will increase, so L will increase. Right? So, what will happen? Right. So, on this, the next graph, when the temperature increases, it will go like this. Curve 2. Do you understand? Why? For the same frequency, now you are going to have a higher length. Higher length because temperature increased. When temperature increased, V increases, velocity increases, frequency doesn't change. So, lambda has to increase. Lambda increases means L has to increase. Right? So, when the temperature increases, graph will take a curve like this. Understood? Because why? We start with higher frequencies. Higher frequency means 1 over F will be low. That means this is where you started. Compared to this, when you go here, temperature increases. Temperature increases. Understand? Temperature increases. So, that is why I said on this side the graph will take upward. Because this is where we are going to have the first reading, second reading, third reading, fourth reading likewise. So, every reading you take, you are going to have a higher temperature. So, graph will take a upward curve. Clear? So, that is a nice question they asked at the end of this part. Usually like if they want to ask something extra, something that you have to think, the last part of this structure question is like that. Not every question will have it. Sometimes they include one part at the end for you to think freshly and answer. That might not be there in any of the previous past papers. A new concept can be tested there. Right? So, this is something like that. We all know when the velocity, when the temperature increases, velocity increases. But then how that is going to affect this resonance experiment, how the readings are going to be affected, that you have to think a little bit at that moment and answer. Apart from that, all other parts were very easy. Now, let us see another paper which is older than this. This is 2011. Let us see now 1991, an older paper. Let us see now. The diagram shows an experimental arrangement used in a laboratory to find the speed of sound in air using resonating air columns. So, the usual arrangement that we have. Briefly explain the procedure that you would follow to find the fundamental resonance of the air column in this arrangement. So, it's a repeated thing that we have been writing. You can simply say, keep the tube immersed in water with only a small height of air column outside the water. Vibrate the tuning fork and hold it near the upper end of the tube. Raise the tube gradually, you can't increase it suddenly, gradually until a loud sound is heard. For the first time, because they said fundamental note. So, you have to highlight for the first time, because there will be a second time as well which is not fundamental note. So, for the first time, this instance will be the fundamental resonance. fundamental resonance. Part B. If the length of air column A is L and the wavelength of sound lambda, write down the relationship between lambda and L. We have written this several times, you know, lambda by 4 equals L. Clearly they have said ignore the end correction. So, E you do not have to write, that is it, lambda equals 4L. Rewrite the formula in B in terms of L, the velocity of sound air V, the frequency of tuning fork N. V equals F lambda, V is V, F is what they say N here, lambda is going to be 4L. Next, you are given a set of tuning forks with known frequencies and asked to find V by drawing a graph. State the quantities that you can plot. So, let us rearrange this. Now, what we have, V equals 4N L. What we can change is these two. So, we will write L equals V by 4 into 1 over N, right. So, the x-axis has to be 1 over N, y-axis it has to be L, the resonance length L. Quite easy ones. Can you see all the basic questions they ask? Waves and oscillation, very less complications you have usually. Quite straightforward questions. Anybody who have done some decent practice on these experiments can do it. The value of L for a particular tuning fork was observed to be 35 centimeter. Is it possible to find another position where the air column resonates with the tuning fork if the length of the tube is 75 centimeter? So, you know lambda by 4 is 35 centimeter. This is for fundamental note. Fundamental note. What will happen next time when you hear the resonance? That is going to be first overtone. First overtone length has to be 3 lambda by 4. 3 into 35. 105 centimeter will be required. 105 centimeter will be required. What is the length of the tube you have? 75 centimeter. But you need to have 105 centimeter above the water. Is it possible with a 75 centimeter tube? No. So, you can say they ask, is it possible? So, say the answer is no. We will write it first here. No, the length of tube is insufficient. Will you expect the L to be greater than, less than or equal to 35 centimeter if the room temperature is increased? Give reasons for your answer. When room temperature is increased, you know velocity of sound will increase. With temperature, velocity increases. V equals F lambda. If V increases, lambda has to increase because F is constant. Lambda increases means lambda is what we call as 4L. Lambda by 4 is L. So, if lambda increases, L has to increase. So, after the temperature has increased, the length at which resonance takes place will be greater than 35 centimeter. So, they are asking, will it be greater than or equal to or less than? Greater than. Greater than. Give reasons for your answer. When temperature increases, velocity of sound in air increases. That is the reason for it. Will you expect the same measurement in 2 if alcohol is used instead of water? Explain your answer. See, instead of the jar with water, if you fill that with alcohol and do this experiment, you know alcohol evaporates in the room temperature itself. So, what will happen, right? If this is alcohol, then the evaporated particles will be here. It won't be a dry air. Water doesn't evaporate that much in the room temperature. Whereas alcohol fast evaporates. It evaporates very fast even in the room temperature. So, near the alcohol surface, you will have the evaporated alcohol molecules, alcohol particles. This will change the composition of air in this place. That means the density is going to change. When density changes, when the composition changes, velocity will change. Right? Therefore, when velocity changes, lambda changes, L will change. So, you can't expect the same answer, same measurement you got earlier. Let's explain that. No alcohol evaporates in the room temperature. The room temperature. The air will have alcohol molecules in it. Molecules. And the density of air will be different. This will affect the velocity of sound. This will affect the velocity of sound. For accurate calculations, end correction should be included to the open end of the tube only. Open end only, not to the closed end. Explain why. You know the vibration is longitudinal. So, when you have water here, the particles here cannot vibrate. They can't vibrate because there is water. So, it won't let it vibrate. So, perfectly at this point you need to have a node. When it doesn't vibrate, you call it a node. But the particles here, they are free to vibrate both sides, right? Because of that, at that point, antinode may not be exactly at the end of the tube. It can be even outside as well. Understand? So, that's what we had to explain. At the closed end, air particles cannot vibrate due to the water level. But in the open end, the particles are free to vibrate. This can result in an end correction. Right, or we can say this can result in the antinode being a little away from the end of the tube. Clear? So, that's another older question. This was from 1991 paper on the same experiment. So, you can see, as I always say, the questions that come on waves and oscillations experiments are quite easy. Pretty straightforward, similar questions they ask every time. There is nothing complicated. Understand? So, if you can just go through this experiment couple of times, remember the experimental procedures we have done and the reasons for the procedures, why we have done this, how we have done this. Right? If you can remember that, understand and remember, then whatever the questions you get in the exam should be easy to be answered. Alright. So, practice this very well. We will meet up again with another experiment in another section.